Hello everybody, today will be our kinematics review. First, we're going to start off by reviewing the importance of defining your coordinate system, discussing the big four kinematic equations, and we're going to do a follow-along problem with a challenging free-for-all situation. So first we have this little stickman guy running on a line. We want to make sure we have a good convention for defining which directions are positive and which are negative. So we always want to define the positive direction with a set of arrows. So I can call this x in the positive direction. Oh, I have that backwards. X in the positive direction and y in the positive direction. Now, once you define these positive directions, you always want to make sure you stick with them. So even if this guy starts running around the other way, you want to make sure that you still consider that this is the positive direction. You would now just describe his velocity to be negative, as an example. So now let's discuss these big four kinematic equations. It's useful to think of these as what you should use in terms of their missing variables, but I would also say it's important to realize where they come from. These first two are derived from calculus. If you would like to solve or derive either of them from each other, you can differentiate or integrate with respect to time, and you will find that those are true. Those are very useful equations when you have time as a variable. The third equation is one that is probably the most unfamiliar of these four, and it is because it uses a physics principle from a later unit on work and energy. Now, this last equation is the displacement with respect to time due to average velocity. Now, let's look at this free-for-all problem. First, let's take into account the variables that we have to work with. Now, we have our initial speed v, given by a velocity vector with an angle theta, and we are having our ball shot out of a cannon at a height h, where it'll eventually reach a spot xf on our x-coordinate system, or xy coordinate system. And we have the positive x direction going this way, and our positive y direction going that way. Now, our gravity is acting downward, and before we even look at these kinematic equations, let's think about the motion of our ball before we get started. And let's remind ourselves what our problem is going to ask us. In this case, I'm going to say that we're trying to find the final speed of our ball as it hits the ground. Notice I said speed, not velocity, but we will still be trying to find our velocity before we find our speed. So when the ball is on this path, at the top, it's going to have a Vy component equal to 0. When it gets to this point, at the same h, I will call this the same h. It's not perfectly represented, but I just meant that it's at the same height as it was within the cannon. It will have a negative v, not y, and when it hits the ground, it will be at, sorry, I should write this too, y equals 0. So if we're trying to find our velocities, our velocity components, I think we should start with this second kinematic equation. We're assuming no air resistance, so when we write Vxf equals Vx naught plus axt, we can write this axt as being 0 because it is not accelerating in the x direction. This term is already done, so we don't even need to worry about this for the rest of our problem, except until we're trying to calculate speed. So now let's look at our Vyf. It's going to be equal to a Vy naught plus Ayt. Now let's consider where we're going to take our Vy naught. We could take it from here, where it is still in the cannon with its very, very initial velocity, or we could take it at the top of its trajectory right here, or we could take it down here, Before we decide, let's plug in our known value for the acceleration, vyf equals vy naught. And let's remember that gravity is pointing in the opposite direction that we consider positive. What this means is that our acceleration has to be negative. So we write minus gt. Now, we're going to consider our vyf, what we're looking for here. And our vy naught is the initial velocity that we're considering. I think we should choose this last one. And the reason I say we should choose this last one is because we already know this value in terms of v and theta. And we could just as well use, we just as well know the value here. However, it will be a little harder to find time at that time. So right, vyf is equal to negative vy naught minus gt. So now let's find the t, the time it takes for our ball to hit the ground from this position. So we've already exhausted the second equation. We can see that this third equation will not help us get time. So let's use this first equation. We're going to have delta y equals vy naught t plus 1/2, not sure why it's lagging so much, ay t squared. Again, let's substitute our known values. Delta y is going to be h, negative h, because delta y is yf minus y initial. Our y initial is h, and our yf is going to be 0. So we're going to have h there when we solve for that. Vy naught t is going to be negative vy naught, because we're looking at it from this point. T minus 1/2 gt squared. So we're going to have negative h equals negative vy naught minus 1/2 gt squared. Let's move everything to one side. And let's multiply by 2 to make this a tiny bit easier. So we're going to have gt squared plus 2 vy naught t minus 2h, and that equals 0. Here we're going to need to use this formula. Negative 2 vy minus minus 4ac, which is going to be plus 8hg all over 2a, which is 2g. This is a very ugly expression. We are going to say that this is going to be positive. This is going to be positive. So we're going to have that t is going to equal squared plus 8hg minus 2vy naught over 2g. Now we have our time, and we can substitute this all the way back into here. So our VYF is going to equal negative y naught minus g times all of this. Now this looks extremely intimidating, but I do want to remind you that you will not be expected to solve questions of this scale on the AP test. I would be very surprised if you were asked to do that. However, I would say that this is a very good exercise in practicing your kinematics skills. So we can cancel our g's here, and we should get that VYF is going to equal negative Vy naught minus 4Vy naught squared plus 8hg minus 2Vy naught all over 2. So now we have our components. We love x. X is extremely easy to get. Remember from earlier, the very first one we did, we got it. And remember that the speed is equal to the magnitude of our velocity vector, which is also equal to our VYF component squared plus our VXF, oh, why did I not write like that? XF squared. And that is how you can get our final speed once it hits the ground. This might be a very unintuitive process or seem unnecessarily complicated. And while I would encourage you to think about kinematics problems more for the sake of practice and to get more comfortable with it, I also want to agree with you. There is an easier way to approach this problem, one that you should be able to come back to after Unit 3 and be able to solve this problem with far less computation and with a slightly different understanding of how to approach it. That way we can double check our answers, and you will feel more confident in your skills in both doing kinematics and in the method you will learn in Unit 3. I hope this helped and that you will continue to